Okay, this is section 2.2, Solving Systems Using Matrices, Part 2. In this video, I want to continue on where we left off in the last video. We solved this system here, and at the end of that video, I showed you how to use the TI calculator's built-in RREF function to compute the reduced row echelon form of the augmented matrix and thus solve the system that way. Now, that's by far the fastest and easiest way to solve a system using your calculator, but sometimes you want to be able to just, while you're learning how to do Gaussian elimination, it might be a good idea to be able to have a way to check your row operations, because they're tedious, and if you make a mistake early on in your sequence of row operations, well, then every single row operation you do after that is not going to help you. It's just a waste of time, really, right? So your calculator has functions built in that will allow you to do row operations on a matrix. And in this video, I'm going to start by showing you how to use those functions. And then we'll move on to the last problem in this worksheet and solve that. Okay, so as you can see over here, I've already, let me make this screen a little bit bigger, but if I hit enter here, I've already put the values in for this matrix, this augmented matrix. Okay, and I'm going to go through the exact same steps that I did. Let me make this just a little bit smaller. But I'm going to go through the exact same sequence of row operations that we did in the previous example and solve this using the calculator. So recall that the first operation we did was we swapped rows 1 and 2. So how do we do that using the calculator? Well, the matrix menu has lots of functions built in, and the elementary row operation functions are right in the matrix menu. So if you go to second and then matrix, and then if I cursor over to math, I'm going to actually go up from the bottom, so I'm going to hit up. Okay, so you see those last three functions, row plus, times row, and times row plus, those are all functions that we can use to do the elementary row operations. Okay, the first one adds two rows together. The second one multiplies a row by a constant. The third one multiplies a row by a constant and adds it to another row. But what we want to do is actually, the one in C, choice C there, is row swap. We want to interchange two rows, okay? And now the question becomes, okay, well, how do I use this function though, Jason? Okay, well, let me see if this works. Okay, whenever you're in the catalog, you can hit the plus key, and it gives you the parameters that the function requires. Okay, so row swap takes three parameters. It takes a matrix, it takes row A and row B. The row A and row B are the two rows that you want swapped. Okay, so by pressing the plus key on your calculator, you can learn what the order, or what kinds of parameters and the order the parameters are required, that function requires. Okay, so now I can just hit escape, which corresponds with the key below, so that would be this graph key. And so I want to put this function into my command window, and I just hit enter, and I have to remember now it comes, I need to put in the matrix name and then the two rows I want swapped. Okay, so the matrix name is, I want to do this to matrix A, so I'm going to hit second and then matrix and then 1. And then I need a comma between parameters, and I want to swap rows 1 and 2. Okay, so there we go. We hit enter, and it does the row operation. However, it does not update matrix A. So, for example, if I go up and fetch A again here, you'll see it's still the original matrix. Okay, so the command creates a new copy of the matrix, and that's the output of the command. It doesn't, in other words, it doesn't mutate or change the original matrix A. And usually we want to store the results. We want to remember the results of the row operation. So how can we do this? Well, I'm going to go fetch the command I just ran, put that back into my command window, and the way we can save the result of doing this operation back into the matrix A is by hitting the store arrow key, which is right next to 1 on your calculator pad. And then I'm going to go fetch the name of the matrix by going to the matrix menu and hitting 1 to get matrix A. So this is what this command does, is it swaps rows 1 and 2 in matrix A and then takes the result and stores it back into A. And then it's going to show us the result. Okay, and there it is. And now we see that row 1 has a leading 1 in it, and the two rows have been swapped. Okay. Next, the next row operation we want to see done is, you can see it over here on the page that we did before. We want to do -3 times row 1 plus row 2 and save that into row 2. Okay, so let's see here. We want to go to, I'm in the command window. I want to go get the command that does that row operation. So I go to second, matrix, math, then I'm going to hit up, and I want to do command F. I want to multiply a row by something. You know what, let's look at the parameter list for this. So let's see here. This command takes a value, the matrix that you want to do the row op on, and then row A and row B. So the value is going to be the value you multiply the row by, and you kind of have to know how this works. It's going to multiply row A by the value you put in the first parameter and then add that to row B. And that's how all of these row op commands work. They always, the second row is the row that's going to get changed. The first row is the one you're using to change the second row. So row B is always going to be the row that gets changed in these commands. And I try to do my notation for my commands, my written notation, the same as the sequence of the parameters in these commands, so that it's kind of easy to follow. Okay. So in other words, our first number is going to be -3, then the matrix A, and then row 1, because we have, in this command here, we have row 1, and then row B will be 2. Okay? So let's see, I need, well, let's escape from this. Okay, I'm going to put this into the command window, and I'm going to do -3, and then I've got to fetch the name of the matrix. Go to matrix, and it's in 1, and then comma. I'm going to multiply row 1 by -3, so I want a 1, and then I'm going to add that into row 2, so I want a 2 here. Close that off. And here, if you're not sure that you've done the command correctly, you could always just execute the command to check, and it won't save anything. But I'm pretty confident that I've done this before, and I'm confident I put the command in correctly, so I'm just going to go ahead and store this result right into the matrix A. And there we go. I've eliminated that 3 that was the leading term of row 2, and now we have a 0. Okay, and now I'm going to use my pivot, that 1 in the top of the first column, to clear out the 1 below it. Okay, so what would this row operation be? Well, I need to multiply row 1 by -1, and then I'm going to add it to row 3. Okay, so I want to use the command in choice F there. And the first thing I need to do is multiply by -1, and I'm going to be doing this to matrix A. And let's see, the row I want to multiply by -1 is row 1, and then I want to add this to row 3. Okay. And then finally I want to store the result in A, so store in A. Okay, hit enter. All right, there we go. Okay, the next thing we did when solving this system is we swapped rows 2 and 3 to get that 1 on the diagonal. We could have multiplied by the second row by -1, but that's what I chose to do. There's no single one way to do Gaussian elimination. Often there's multiple correct paths. Okay, so let's do the row swap. We're going to go to the, let's see, I want row swap. There we go. And remember, this command, I'll just show you again. You hit plus. Okay, it takes the matrix and then the 2 rows that get swapped. So I'm going to put this into the command window. The matrix is matrix A. And then I'm going to swap rows 2 and 3. So 2 and 3. And then store the result in A. There we go. Great. Okay. Now I'm going to use that 1 that's in the second row, second column, to clear out the -1 below it. So here I just have to add 2 rows. So I'm going to go to the matrix menu, math, up, and I'm going to choose choice D. I just need to add 2 rows together. Let me pull up the command. Yep, matrix, and then the 2 rows that you're adding together. With the second row, remember, it's always going to be the second row is the one that's going to get changed. Okay, so I put that command into my command window. The first parameter is the matrix name, which is A, and then comma. I'm going to add row 2 to row 3. So 2 first, and then comma 3. And then I'll store that result into A. Just make sure I've done this correctly. That looks right to me. Okay, good. Next, I want to get a 1 on that diagonal element that is currently a 12. So I need to multiply a row 3 by 1/12. So let's see, that's going to be in the matrix, math, up. Let's see, that's choice E. I just need to multiply a row by a non-zero constant. So the value is 1/12. So 1 divided by 12, comma, and then the matrix name, that's 1, and then comma, the row. I'm going to multiply row 3 by 1/12. Okay, and then store that into matrix A. Okay, that looks correct to me. Hit enter. Yep, that did what I wanted it to do. Okay, I have 2 row operations left. I'm going to multiply row 3 by 2 and add that to row 1. Okay, so matrix, math, up. I'm going to do choice F. and I'm going to multiply by 2. And the matrix name is A, comma. Okay, now the rows. I'm going to multiply row 3 by 2. So 3, and then I'm going to add this to row 1. All right, and then of course store the result into A. Double check. Yep, multiply row 3 by 2 and then add that into row 1. That's good. Almost done. One last row operation. I'm going to multiply row 2 now by -3 and add that to row 1. So we go to matrix, math, up, enter. Okay, so make sure you use the unary minus, the negative, whoops, delete that, okay, comma. So my multiplier is -3. The matrix I'm doing this to is matrix A. And I want to multiply row 2 by -3, so I need a 2 here, comma, and then I'm going to add this into row 1. And we'll store the result into matrix A. Okay, I think that is correct. Hit enter, and there we go. Yes, we do get the same exact solution as before. So this is a great way to check your work as you go, or just if you want to do it all by hand. This can be extremely useful. All right. Okay, next exercise. Find the solution to the following system using Gaussian elimination to obtain the reduced row echelon form of the augmented matrix. Okay, so we want to first make an augmented matrix. Let's see here. I don't need the calculator for this right now, so let's hide that. So our augmented matrix will be 1, -1, -4, and then 0, and then -2, 3, 11, 4, -3, 5, 18, 8. Okay, I'm going to use a slightly different notation for my row operations than I did before. Something that's a little more compact. Okay, so the first thing I want to do is use I have a 1 on the diagonal there in the first row, first column. I'm going to use that to clear out the -2 and the -3. I'll clear out the -2 first. And so what I want to do is I want to do 2 times row 1 added to row 2. Okay, in my previous notation I would, use this arrow and say store that into row 2. But as long as we use the same notation as the calculator and just remember that the row that comes second is always going to be the row that gets modified, then that little arrow is superfluous. We don't need it. So let's switch to this more compact notation. Okay, what is 2 times row 1? 2 times row 1 is going to be 2, -2, -8, and 0. And I'm going to be adding that to row 2, which is this one. Top row stays the same, 1, -1, -4, 0. The second row, though, becomes 0, 1, -8 and 11 is 3, and 0 and 4 is 4. Third row stays the same at -3, 5, 18, 8. Okay, now I'm going to use that 1 to clear out the -3. So I want to do 3 times row 1 added to row 3. And we'll write the result here. Okay, 3 times row 1, I'll write that up above. That's going to be 3, -3, -12, and 0. And we're going to add that to row 3, which is that row there. So first 2 rows stay the same. 1, -1, -4, 0, 0, 1, 3, 4. And then the third row changes, though. We get 0, -3 and 5 is 2, -12 and 18 is 6, and 0 plus 8 is 8. Okay, the next row operation we want to do is we want to clear out this 2 using the 1 above it. So we want to do -2 times row 2 and add that to row 3. Okay, -2 times row 2 is going to be 0, -2, -6, -8. We're going to add that row to the bottom row here. And when we do this, we'll get, top row stays the same, 1, -1, -4, 0. Second row stays the same at 0, 1, 3, 4. And the third row becomes 0, -2 and 2 is 0, -6 and 6 is 0, -8 and 8 is 0. Okay. So we have a row of all zeros in our matrix. What does that mean? It means that, well, it means that we have an infinite number of solutions to the system. But how do we represent such a system? Well, this matrix is in row-echelon form, but it's not quite in reduced row-echelon form. What we want to do in this situation is still continue on until we have the matrix in reduced row-echelon form, and then we want to do the parameterization algorithm. I'll show you that when we get there. Now, if you look at the first column, there is a leading 1 in that column, but all the other elements are zeros, so that qualifies for reduced row-echelon form. But what about the second column? There is a leading 1 in the second row there, but there above that leading 1 is not 0, it's -1. So we need to make that a 0. Okay? Notice this 3 is not a leading coefficient. So, and there's no leading 1 in that row because of the row of all, or sorry, in that column because of the row of all zeros below it. So we don't need to, there's no way, in fact, to eliminate the 3 and the -4. We can't do it. We don't have a pivot. But we can eliminate the -1 in row 1. So how are we going to do that? We're going to do, well, we just need to do row 2 added to row 1. Okay. And we're going to get 1, 0, 3 and -4 will give us -1. 4 and 0 will give us 4. Second row stays exactly the same. 0, 1, 3, 4. Third row is just all zeros. Okay, so this matrix was in row-echelon form, but not in reduced row-echelon form because of that -1. But now this matrix is in reduced row-echelon form. Okay, and once we've put our matrix into reduced row-echelon form, we can begin the parameterization algorithm. So the first step is we want to write the rows that are not all zeros as equations again. Remember, this is the x column, y column, z column, and the constants column. So that first row corresponds with the equation x plus 0y minus z equals 4. The second row of the matrix corresponds with 0 times x plus 1 times y, so y plus 3z equals 4. Okay. And I want to keep my variables in columns here. Now, so notice that since the z column does not contain a leading one coefficient, z is a free variable, okay? Meaning that it can take on any real value, and we can still find values for x and y such that these two equations will be satisfied, and indeed the whole system will be satisfied. So to emphasize that z is a free variable, we rename it to usually t. Okay? And so what we're going to do is rewrite the system replacing z with t. Okay, and we want all of the original variable names on the left. So I'm going to rewrite this system with, well, first we'll just move all the z's over to the right-hand side with the constants, and we get x is equal to z plus 4. And then y is equal to negative 3z plus 4. Okay. And now we'll do the replacement of z with t. Okay. And we need to remember to put in this parameterization where we're setting z equals to t. A lot of students forget to do this and get confused. So x is now we're going to replace all occurrences of z over on this side with t. So we end up with x equals t plus 4, and y equals negative 3t plus 4, and z equals t. Okay. So, and the idea is t is a free parameter. It can be any real number. Okay? Any real number. So one way to think of the solution set is it's the set of all points where you have t plus 4, negative 3t plus 4, comma t, such that t is just any real number. Okay? So there's the solution set. We have to use the parameterization, and because t can be any real number, there's an infinite number of solutions. And what this solution set is it's a line in a three-dimensional space. So for every, think of it like t, think of the parameter t as time, and that's why we use the letter t. So at time 0, if we evaluate for x and y and z, we'd see at time 0 the x-coordinate is 4. The y-coordinate is 4, and the z-coordinate is 0. So at time 0, you're at point 4, 4, 0 in three-dimensional space. And then if you go 1 unit in time, forward in time, then you're going to be, your x-coordinate will be 5. Your y-coordinate will be negative 3 plus 4, will be 1. And then your z-coordinate will be 1. So 5, 1, 1. Yeah. 5, 1, 1 is the position you'll be in three-dimensional space at time 1. And you can go backwards in time as well. And so the solution set is just a line in three-dimensional space. Another way to see this is to take this set of equations, these parameterized equations, and we're going to rewrite this as a matrix equation. I'm going to rewrite it like this. my column vector of variables x, y, z is equal to, let's see, what are those coefficients of t? I've got 1 times t, negative 3 times t, and 1 times t. If I think of this right-hand side as having columns, right? That column containing t, the coefficients of t are 1, negative 3, and 1. So I'm going to rewrite this. I'm going to factor the t out and just have it multiplying this column vector containing 1, negative 3, 1. And then we have to add on this column vector of constants 4, 4, 0. Because there's an implied, we could put plus 0 right there. Okay? All right. So think of it like this. I have this vector x, which is my position, which is a function of time times this vector u plus this vector v. Okay? So the way to think of this in three-dimensional space is, let's see, if I get a set of coordinate axes here. We'll push those to the back, order, send backwards. Okay. So now the way to think of this is, okay, so I have this v direction. Okay, maybe v is often, say, that direction. Okay. So the v vector, it's just an arrow. You can think of these numbers 4, 4, 0 as giving me coordinates in space. And if I draw an arrow from the origin to that coordinate in space, it defines an arrow. Okay. Same with this u vector, 1, negative 3, 1. Okay. And maybe that u vector is, if I were to draw it, maybe it points off, say, in, so let's say the u vector points off in this direction. Okay, there's my u vector. Okay, what I'm going to do is translate that u vector so that its tail is at the tip of the v vector. Okay, so let's see, it'd be like that. Okay, so here's a u vector, and that's going to get me to this point. Okay, and if I take another copy of the u vector and put it right here, it's going to get me to this point. And then I could do the same thing. I can take another copy of that u vector and put its, almost the same thing, put its tip to the tail of, or sorry, to the head of the v vector, and then just keep taking copies of u like this. These are all just copies of u, right? But put tail to head. Okay. Now, what is this? Notice that the u vectors form a line in this three-dimensional space, and this point here at the tip of the vector v corresponds to t equals 0. But if I move 1 unit forward in time, I'm going to get to this location in space. This would be t equals 1. If I let the time tick one more time, I'm going to get to this point. This would correspond with time t equals 2, and so forth. And then over here, this would correspond with going backwards in time, negative 1 unit in time. This would be backwards in time 2 units. So I'm using u because that's the unit of time. Oh, well, the unit vector in the spatial dimension that corresponds with that much time elapsed. Okay? And so we see that this is indeed, it's a line in a three-dimensional space. My drawing is not great, but you hopefully get the idea. Okay? So that's one way to interpret this solution set. This is a way of determining the points in a three-dimensional space that are on a line. Okay, and notice that each one of these coordinate functions in the solution set is just a linear function of t. You've got a slope and a y. Well, in this case, it's going to be x-intercept, y-intercept, z-intercept. Okay, so that's it. Okay, and that's the end of section 2.2.